You know, I've always been fascinated with mechanical metronomes and clocks. It seems magical the way they can keep perfect time with just a few springs and gears.
Oh, they are cool, but it's not magical, it's mathematics. Clocks and metronomes are based on the way that pendulums work.
Yes, and a simple pendulum is a mass called a bob, suspended at the base of a rigid arm. Now, a simple pendulum considers the mass of the arm to be 0.
And a simple pendulum swings back and forth in a very precise time, determined by the length of the arm.
Each swing back and forth is called the period of the pendulum. See?
Mm-hmm.
And if the length of the pendulum is measured in centimeters, then the period is 1/5 of the square root of its length.
Let's see.
Okay, let's try this low to start.
Huh. So in this case, the pendulum swing is 1.6 seconds. And since the length of the arm is 64 centimeters, the data matches the formula.
Excellent. The interesting thing about this formula is that it does not depend on the arc of the pendulum swing. It still takes the same period of time.
Let's see.
All right. You ready?
All right.
Try it a little higher this time.
Still 1.6 seconds. And that's why pendulums are used to run clocks and metronomes, because they keep precisely predictable time.
A metronome is still a pendulum with the bob and the arm below the pivot point.
And it also has a sliding weight above the pivot point.
This is an example of a compound pendulum.
Compound pendulums still have precisely predictable periods, but now the mass is no longer at the center of the bob.
So that means that the period is related to a point called the center of mass, and the distance from that pivot to the point.
Here we have a straw with 2 different weights at the end. And I can find the center of mass by balancing the straw on a point.
Now, if we move one of the weights, or change it, then...
I have to shift the center.
Yeah, the center of mass changes as well. Let's see, can she get it?
Found it.
Ah, she got it. Very good.
And that is how a metronome works. By changing the position of the sliding weight, you are effectively changing the center of the mass of the pendulum.
That changes the distance from the pivot to the center of mass, and the period of the pendulum changes.
When the sliding weight is closer to the pivot, the center of mass is closer to the bob. Now, since the center of mass is farther from the pivot, that has increased the frequency of the periods.
Huh. And then, if you move the sliding weight away from the pivot, then the center of mass moves away from the bob and closer to the pivot, and the period decreases. Pretty cool, huh?
Mm-hmm. Now, see the marks on the metronome? They're not evenly spaced.
But that's because the period is related to the distance of the square root. So the marks are actually spaced according to the square root function.
Each time the pendulum swings to one side, it advances a gear within, which causes that ticking sound.
And the ticking sound is actually made by a device called an escapement. Escapements are devices that move gears inside, and they can be found in metronomes, clocks, and other timekeeping devices.
But only the motion of the pendulum affects the timing, which you can see by moving the sliding weight. See? It's a mathematical machine.
Ah, or is it a magic-matical machine?